Okay, and let's introduce the last talk of this session, Jijun Zhu, probing short-range polar order in PZNPT and PMNPT relaxer ferroelectrics with neutron scattering.
Yeah.
So I'll go like this to tell you 5 minutes left.
Okay. Thank you, the chairman and the organizers. It's my pleasure to be here to give this talk, and I come from NIST Center for Neutron Scattering and the University of Maryland. Let me first thank my collaborators here, Dr. Guangyong Xu and Peter Gehring, also from NCNR, and Chris Stock from University of Edinburgh, and Fei Li from Penn State. Thank you for the nice single crystal sample. And Sujun Zhang from University of Wollongong, and Zuo Guangye from Simon Fraser University. Our results are focused on two lead perovskite relaxer ferroelectrics, the PZN and the PMN, by doping with lead titanate, the PT. This system shows extraordinary piezoelectric and dielectric properties and make its considerable importance in technology. And the phase diagram of PZN XPT and PMN XPT are quite similar. At low temperature, the doping changed the rhombohedral structure to a monoclinic MPB phase, and in this talk, we will focus on doping on the left side of the MPB phase. And one unique structure in this relaxer system is the polar nanoregion, PNRs here, which is first proposed by Burns and Deckholz in 1983. And this nanometer-sized local polar region appear at Burns temperature, TD, which is higher than TC. And the PNRs grows with cooling and persist into low temperature. Since the PNR are atomic deviation from their perfect position, so we can use diffuse scattering measure then by neutron or X-ray. Here is an example of measurement of PMN at 200 K. Around 100 Bragg peak, we can see a butterfly-shaped diffuse intensity distribution extend along 110 and 1-10 direction. And around other Bragg peak, like 110 Bragg peak, there are just only one wing, but the intensity still distribute along 110 type directions. And in neutron diffuse scattering, the intensity are proportional to Q times epsilon, the atomic displacement square. So the red wing here around 110 Bragg peak should mainly come from local polarization along 110 direction. And the local polarization along 1-10 direction will contribute to diffuse scattering along 1-10 Bragg peak. And near 100 Bragg peak, there have contribution from both the red and the blue wings. Here are some our recent results in the PMN28PT single crystal, measured at 100 K in the HKO plane. Around 100 Bragg peak, we can see clearly a butterfly-shaped diffuse scattering, have both red and blue wing. And near 110 Bragg peak, mainly is from the red wing, but there are still some intensity from the blue wing, but much weaker. And near the 1-10 Bragg peak, it's similar, but on the opposite way. To better understanding the data, we also try to do a linear scan, which it's a K-scan at h equal to 1.1, which cross the field scattering and avoid the strong Bragg peak. As we expected, for in zero field cool, the contribution from both red and blue wing should be equal or similar. And we see a symmetric two peak here. And from this scan direction, the left peak always from the red wing, and the right peak always from the blue wing. And near the 110 Bragg peak, we will see that the peak from red wing is much stronger, but still have some intensity from the blue wing. And near the 1-10 Bragg peak, the situation are similar, but on an opposite way. And also, we do some temperature dependence from 100 to 500 K. The intensity increase with cooling, but even at 500 K, which are above TC around 375 K, the diffuse scattering intensity is still there. And as we know, the diffuse scattering in the relaxer are easily affected by applying an external field. For example, in this case, we try to apply a 2 kilovolt per centimeter electric field along 110 direction. And then the diffuse scattering near 100 Bragg peak are clearly asymmetric now. The blue wing seems much stronger than the red wing here. And near the 110 Bragg peak, also the blue wing are much enhanced, and it's almost same intensity as the red wing here. And for the diffuse scattering near the 1-10 Bragg peak, the strong blue wing is even stronger and become dominant. And we just do some similar linear scan as before. And since we know that from the mesh scan, the electric field seems enhance the blue wing and suppress the red wing, and the intensity will look like this. For the scan near 100 Bragg peak, we see a clearly asymmetric two peak, and the right peak from the blue wing are clearly stronger than the peak from the red wing. And for the scan near 110 Bragg peak, the weak peak from blue wing are enhanced by the field, and at low temperature around 100 K is almost similar intensity compared to the peak from red wing. And near the 1-10 Bragg peak, the strong blue wing is even stronger, which cross the top. And so here we have an idea that the 110 field will enhance the blue wing, which coming from the local polarization along 1-10 direction, and suppress the diffuse scattering coming from local polarization along 110 direction. And how about in other zone? For example, in the HOL plane, it similar have also polarization along 101 and the 10-1 direction, and have the similar diffuse scattering pattern in zero field. By apply the same 110 direction electric field, the field cool have no clearly effect compared to the zero field cool data. It's both the case around 110 Bragg peak and 1-10 Bragg peak. So it seems the 110 field have no effect on diffuse scattering coming from either the 101 polarization or the 10-1 polarization. And it's also the same case if we measure in the 0 KL plane. So the 110 field effect have no effect on this four kinds of diffuse scattering from local polarization. And here are a summary of field effect in this system with different kind of field. And for here, we list 6 diffuse scattering associated with 6 different local polarization along 110 type direction. We just show the 110 field will suppress the diffuse scattering coming from 110 polarization and enhance the diffuse along from polarization along 1-10 direction and have no effect on other 4. And we know the 111 field will enhance 3 kinds of diffuse scattering and suppress other 3. And the 001 field have no effect on either of the 6 type diffuse scattering. To understand this, we use a model we proposed before that at high temperature, the PNRs are almost random. By zero field cool, the ferroelectric domain is established along different 111 direction, and the 110 type polar nanoregion tend to align perpendicular to the 111 polarization of their surrounding ferroelectric domain. But if we field cool in a 111 field, the ferroelectric domain along 111 direction will become dominant, and it will enhance all 3 diffuse scattering coming from 110 type local polarization associated with this domain. Let's see how we use this model to explain our result. We have 4 different kinds of 111 ferroelectric domain, and each coupled to 3 local polarization perpendicular to them. And in the zero field cool, the population of each ferroelectric domain are almost similar, and so the contribution of each 110 type diffuse scattering are also similar. So they show average similar 6 different type diffuse scattering. And if we apply a field along 001 direction, it have no prefer on certain ferroelectric domain, and so the population will keep similar and nothing change. So the 001 field have no effect on either of the 6 110 type diffuse scattering. But if we apply a field cool in a 111 field, it have a preferred domain of the 111 domain and suppress other 3 domain. And it makes the 3 polarization associated with 111 domain enhanced and suppress other 3 kind of diffuse scattering coming from local polarization not associated 111 domain suppressed. And let's also see how is the field effect along 110 direction. For the 110 field, we'll prefer 2 domain along 111 and along 11-1, and don't like other 2 domain which perpendicular to the field. And in this case, the 1-1 diffuse scattering from 1-1 polarization will have 2 double source, will be enhanced, and the diffuse scattering from polarization along 110 direction have no source, will be suppressed. And all other 4 still have an average 1 contribution, and so it will be keep almost same. And here is the summary of my talk. The local 110 polarization tend to align perpendicular to the 111 polarization of the surrounding ferroelectric domain. And moderate field appear to mainly affect the macro ferroelectric domain itself, which have polarization along 111 direction, rather on the local polar order PNR directly. It's the end of my talk. Thank you for your attention.
Okay, this is very nice. And we do have a few minutes for questions, so please come up to the microphones. And while you're getting there, I'll sneak in a quick question. How rapidly does this change with composition, this picture that you have of the zero field cooling and the finite field cooling? If you change from 28% to 30% or to 25%, are they all extremely different or are they all similar?
General, on the left side of MBP phase, they are quite similar.
Yeah. I see. Okay. Anyone else have some questions? Maybe you're all ready for lunch. Okay, well, we really heard a lot of interesting new ideas this morning, so let's thank all the speakers.
Thank you.
This was very nice work. Thank you. Yeah. No, that's okay. So we have this recent paper about relaxer ferroelectric domains. Yeah. Maybe we can analyze it in terms of 111 and 110 type polar nanoregions. I think it's a good idea. We only did zero field cooled. We didn't really apply big fields. I'm glad to know about you. It's a very good work. Okay, I thought it was very enjoyable.
I work with